This is the third video in a sequence that I'm making for teachers who might be thinking of teaching geometric algebra at the high school level. The previous videos in the sequence, I'll link them either on the screen or in the video description. By the end of this video, the teachers will have some background to help them demystify the subject of bivectors for their students. For example, how can you have a circular bivector if bivectors are parallelograms whose sides are straight vectors? Also, how can you use bivectors to specify a given plane if bivectors themselves do not possess the attribute of location? We'll take a look at that now just a bit as a preview. Here we have a bivector, a generic one here, the circle. It's a section of a plane, and it has a rotational orientation, or rotational sense is the term I'll use. So how could we specify a bivector based on, or a plane rather, based upon that bivector? Well, what we do here, I'll add this plane here, just the regular XY plane, to help us with our depth perception. And we're going to construct a plane here, or specify it, I should say, as passing through this point P. So how do we do this? Well, in geometric algebra, what we do is specify that all the vectors parallel to that plane, or all the vectors, I should say, in that plane, are also parallel to the bivector. So we'll just crayon in a few here. So all these vectors are parallel to the bivector, as we can confirm here. Geometric algebra, for those who aren't familiar with it, is a highly effective extension of vector algebra. It was invented in order to capture geometric aspects of reality in a form that's amenable to algebraic manipulation, and it's quite efficient. This geometric algebra was not arrived at overnight. It was a product of an awful lot of thought, and still it's not difficult to use. It's very efficient, and it can be introduced effectively at the high school level. In fact, there's a LinkedIn group dedicated to that purpose, and I'll put the link in the video description. One of the members of that group, Professor Philippe Hénin, has noted the need to convince high school teachers of GA's advantages for teaching STEM subjects. And of course, as part of that, we need to provide teachers with a background to give convincing answers to the students' questions. So, bivectors, we looked at that a little bit here. Bivectors are an important and really neat part of GA, and they have several different uses. The teachers, they'll want to know how they can teach this subject, and the advice I'd give to students, and of course to teachers to pass along to students, is to not try to guess bivectors' properties from a mystical idea about bivectors being oriented portions of planes. Instead, let's understand first, or as a route to understanding bivectors, understand the types of problems that this idea was intended to help solve. And in this way, we can understand the choices that GA's developers made regarding which properties they'd associate, or with which properties the bivectors would be endowed, and why. So let's look at torques. Now, we're going to look at torques as a physical, practical example, a concrete one, but we want to emphasize that once we've explored real problems that give rise to the idea of bivectors, there's much to be gained by playing around with bivectors as purely geometrical objects, and we may repeat that as we go through here. So, let's take a look at a torque situation here. We have a cylinder with a rod sticking out of it, and two forces acting upon the rod. Now, we know that the torque produced by F2 here is going to be kind of like that, and the torque produced by F1 is going to be more like that. So torques have a directionality, in a sense, that we want to be able to capture through our mathematics that we use to describe them and calculate with them. So the typical idea here is that if we're going to use vector methods, first we represent that lever here as a vector, L. And the traditional way of dealing with torques is via the familiar cross product. The cross product, L cross F, gives us a vector that is perpendicular to the plane of the force and the lever. And here we're dealing only with force 1. We won't go into force 2 anymore. And the magnitude or length of that vector is, given by this formula here. So anyway, the developers of geometric algebra had a different idea. Instead of specifying kind of this orientation and direction of the torque by means of a vector, they said, well, let's represent it by a chunk of the plane that contains both the force and the lever. And they'll use, or what they did was, they assigned a sense of rotation to that plane, and the area of this chunk of plane here represents the magnitude of the torque. Now we need to talk about what I mean by the area here. And we're all familiar with the graphical addition of forces. To add two forces graphically, well, we choose some convenient length here to represent the length 1, or to represent the force 1 Newton. We draw the two vectors that are to be added in proportion. So this 3 Newton one is 3 times longer than the 1 Newton, and the 5 Newton is 5 times longer than this. And then we draw the resultant here and figure out its magnitude by scaling it against this, or using this as a unit of measure. This would probably be about 1, 2, maybe 3, 4, 5, 6, maybe up towards 8. So in this idea of using areas to represent torques, what we're going to do is something similar. For the length of the lever, or the length of the vector L, we choose some convenient length here to represent 1 meter of length of the lever, and some other convenient length here to represent 1 Newton of force. And this area here would be, in this case, 6 times 3, 18 Newton meters. So what we're doing in effect back here in this idea of using the area of the rectangle formed by the lever, or by the vector L and vector F to represent the torque, is we're using the plane that contains these two vectors as kind of a whiteboard to do this little diagram. Now let's look at that rectangle, examine it in order to figure out what properties a bivector or that rectangle must have in order to represent torques. Well, first let's put the torque in here, its direction, and let's draw a rectangle. So the area is equal to the magnitude of the torque, and here we have the direction. And one thing we'll notice right away here is we've drawn this force as being perpendicular to the vector L, to the lever. But we also know, from the physical nature of torques, that any vector that has the same component perpendicular to L here as the red vector is going to produce the same amount of torque about the pivot. So this tells us that, okay, we can't restrict this area here to being a rectangle. In this case, at least, it's a parallelogram, but in any case, we can't endow these things here, these areas, with the property of shape. Also, let's look at a few more things here. How are we going to denote the sense of the rotation? Well, one way to do this, and it is what the geometric algebra developers did, they looked at this and said, well, look, going from L to F, that's the direction of turn. That's the same direction as the torque, so let's assign to this area here a sense of direction that's the same as the sense of the turn from L to F. And this now is what we call a bivector, and we represent it by this wedge symbol. So L wedge F is equal in magnitude to the area of this parallelogram, and its sense is the direction of the turn from L to F. There's a few other properties of torques that we need to make sure we're accounting for here, so let's examine them a bit. Let's put a reference frame here. Well, one thing we know is that the pivot here, or the torque around the pivot, is not interested at all in what the reference frame is. This thing is being twisted. So the area, of course, here in the sense of rotation is defined in this way and by geometric algebra, does not depend upon the position, and it doesn't depend upon the precise nature or the precise reference system that we're using. E1 and E2 here are two vectors. More commonly, at the high school level, they might use X and Y or I and J. But anyway, here you can see as we change the reference system, the precise components of F and L change, but they don't affect the bivector. They don't affect the sense, or these changes in reference system, I should say, don't affect the sense, and they don't affect the magnitude. So that's great. That all checks out. We haven't introduced any problems for ourselves. What if we reverse the direction of the force? Well, of course, that's going to reverse the direction of the torque. And is that consistent now still with the idea of the turn from L to F? Well, yes. Now the turn from L to F is like this instead of being like that. So once again, the torque that's produced has the same sense here as the turn from L to F. So this is all great. This works out fine so far. So just as a recap here, the magnitude of the torque is represented by the area of the parallelogram, and let's go back and make sure we know what that area of the parallelogram means. It means this, the diagram we've drawn on the plane that contains L and F. And also, the sense of the torque is in the direction of the turn from L to F in either direction of the force. So that's all great. At this point, the students may ask, are we actually accomplishing anything or just playing around? We've said that bivectors do not possess the attributes of location and shape, only area and sense. So this question as to whether we're accomplishing anything or just playing around here is legitimate, especially because a key element in geometric algebra is that these vectors and bivectors really do have geometric interpretations. So, to answer the student's question here, one thing we have to look at is that if we want to use bivectors to represent torques, then there'd better be a geometric operations corresponding to situations like the following here. Here we have two forces, Fa and Fb, acting upon or acting at the end of a lever, the vector L. So for simplicity, we'll just treat the case in which the lever and the two forces are all coplanar. Each of these forces will produce a torque about this end of the lever down here, and we can represent each of those torques by a bivector, as we've seen. Okay. Physically, we know that the result of this loading here, or the application of these two forces at the end of L, at the end of the lever, the result is just going to be a single torque, of course. So what geometric operation will produce the bivector that represents that single torque? Remember, we're saying that we would represent the torques by bivectors, so how do we do that in this case? Or are the students right and just playing around? So, let's look at this a bit. This is a bivector for the torque produced by force A. bivector produced by the force FB. Now, if we look at those, both of those are in the same, or have the same sense here. So the bivector that will have the, or that will represent the resulting torque produced by the two of these will be this area here. We just stick these two areas together and the resulting total area is the magnitude of the torque. There we have it. And it's in this sense, the same sense as the other two bivectors. So this is the bivector that represents the torque. The only thing is it's not in a form that's remotely useful to us for calculation. So let's look at this a little more, remembering again that the only characteristics of a bivector are area and sense, and in a three-dimensional case, the orientation, the precise sort of plane that it's parallel to. So let's look at this again. Here we have an area, but what's it composed of? Well, it's composed of this parallelogram and this parallelogram. Both of them have the same base length. So they have the same base length and their respective heights, and their respective heights are the perpendicular components of the respective vectors here. And put together, these two perpendicular components are that high. So using our geometry, we can show that this whole hexagonal bivector here, this is a hexagon, has the same area as a parallelogram that has this base and that height. Well, looking back at this, what is this side? Well, it's a vector sum of FA and FB. So by definition, this parallelogram here with this orientation, remembering this is the sense of the turn direction, this bivector here is L wedged with the vector sum of FA and FB. So this makes sense. Physically, the torque produced by the combination of these two vectors FA and FB will be the same that it would be produced by the vector sum of FA and FB. That's great. And before we leave, I want to emphasize again, this bivector and this shape here, I should say, I'll go back here. This shape here, this hexagon, and this parallelogram are identical bivectors according to geometric algebra. They have the same area and the same sense of rotation. So we should note here, and this again is something we mentioned, it was through an examination of the physical properties of torques that we identified some of the mathematical properties that bivectors must have in order to be useful for representing torques. Back to our question, how can you have a circular bivector if bivectors are parallelograms whose sides are straight vectors? Well, here we have the answer, and I'll just let you read it. There's no such thing as a circular bivector or a parallelogram one. I'll let you read this. The shape of the area that represents the torque or whatever is usually of no significance. I'll let you read this. So bivectors aren't used for representing shapes. We have other ways to do that. Another question here that students might have is, well, have we outsmarted ourselves and made bivectors too generic to be really useful? For example, how can you use bivectors to specify a given plane if bivectors themselves do not possess the attribute of location. So we'll look again at what we took a peek at earlier here, and that is this situation. Just a bivector here, and I've just drawn it. I've just drawn the bivector at the intersection or at the origin of this XYZ set of coordinates. So here's how we can, again, how we can make a plane parallel to this bivector, or use this bivector to specify the orientation and the plane that passes through a given point. Here's our given point P, and the way we do this, and in geometric algebra there are very convenient, very efficient ways to do this. We say, all right, the plane that we want through this point and parallel to this bivector contains only those vectors that are parallel to the bivector itself. So here's one of them, and to generate that plane, we'll just crayon this thing around here a bit till we get enough to actually be visible or to be intelligible. And there we have our plane. It contains only the vectors that are parallel to the bivector that we used to help generate this. So that's a very efficient way of doing this for many problems. So we can satisfy the students on that point. And I should mention here that we want to emphasize to students that geometric algebra isn't just these beasts that are called vectors and bivectors, etc. It's also, or GA is also a set of operations that enable us to use those objects together to express geometric aspects of reality in forms that are mathematically convenient. And again, it was from considering the bivectors at geometric algebra considering bivectors as geometric objects that we got this idea. This was not from torques, or this idea, we didn't get it from playing around with torques. We got it from considering the bivectors as purely geometric objects. So, to finish up here, advice to students is don't try to guess the bivector's properties from some mystical idea about bivectors being oriented properties or portions of planes. Instead, start by understanding the types of problems that this idea is intended to solve. And in that way, we can also understand perhaps the choices or why GA's developers made the choices that they did regarding the properties with which bivectors would be endowed. Again, there is a group in LinkedIn that's dedicated to helping students at the high school level and their teachers, and I look forward to your comments.